Hello everyone, we are group 2. Our group is interested in the flow visualization of airfoil with the variation in angle of attack. My name is Triet. I will present the introduction and background and our proposal for the project. Matthew will present about planning and manufactures of the airfoil. Josue will present about our MATLAB simulation. Yonghao will present the X-foil simulation. Tristan will present our experimental setup. Noah, Vanessa, and Kevin will present the result. Dev will present the streamline manfoil. And finally, Xuanqi will present final observation and conclusion. We are interested in airflow through an airfoil at different angle attack. There exists current simulation already, such as RENS, LES, and DNS. However, they have several limitations because they depend on the solution of the Navier-Stokes equations. The full solution is very computationally challenging. Therefore, simulation usually use assumptions like incompressibility or inviscid flow. This simplification leads to discrepancy between simulations and actual airflow behavior. Therefore, in this project, we want to experimentally show the flow visualization through an airfoil at different angle attack. If we look at the Naraki 00112 airfoil at angle of attack 10 degree, we start to see the trailing edge star at 15 degree, we get the leading edge star. And then finally, if angle of attack is high at 20 or 30 degree, we can see the fully separated flow. For our proposal, based on the existing publications, we expect the data to show a clear flow attachment at low angle of attack with smooth streamline and minimal vortex formation. As the angle of attack increase, we anticipate visible flow separation and the development of turbulent region near the trailing edge. Next, I would like to hand this off to Matthew for planning and manufacturers of the airfoil.
Hello, for our model, we chose the NACA 0012 model. What is a NACA 0012? The 00 just indicates that there is no camber or curvature, and the 12 just indicates that our thickness to chord ratio is 0.12. Some design constraints we faced were fitting the airfoil in the test section. We needed to make sure that the airfoil fit comfortably in our wind tunnel. And another constraint was that the airfoil needed to be printed in 2 parts due to the size of the 3D printer. An initial design approach we considered was putting the airfoil sideways to view and record streamlines from the top, but this ended up not working because we would not have been able to change the angles of attack. Next, I will hand it off to Josue for the simulation.
Xfoil is a rudimentary program which is capable of calculating the velocity components around an airfoil by inputting individual coordinates. However, by integrating it with MATLAB, it allows for the creation of a script that will input the points of a pre-established grid and then graph the velocity components through the use of the stream2 function as seen on the top right. Although Xfoil allows you to arbitrarily set the angle of attack, if the angle is high enough, once it's visualized, it displays signs of stalling through both warped and even incomplete streamlines as seen in the bottom right. Lastly, since the blockage effect, in effect where the stream closest to the test object is accelerated due to compression, is a concern within the wind tunnel, appropriate sizing is necessary to minimize this effect as best as possible. This can be approximated visually through the simulated streamlines in where you look for the general point at which the streamlines are mostly unaffected and closely resemble the free stream, or alternatively, it can be calculated through the comparison of velocity components. I'll pass it on to Yonghao for Xfoil.
Thank you, Josh. So this is our sample simulation on our Xfoil for our NACA 012 airfoil. So this is Xfoil is for the 2D airfoil simulation. The left part is for the friction coefficient distribution. We run it at the Reynolds number when the Reynolds number is 100K and our angle of attack is 3 degrees. You can see that there's some section that the friction coefficient is negative. That means separation occurs. So we can see that there's some slight separation bubble occurs on the top, but disappears as transition occurs. That means laminar flow goes to turbulent flow. And the plot on the right is the pressure coefficient distribution and also the boundary layer distribution. And we run it at a Reynolds number 100K as well, and the angle of attack is 5 degrees. And we can also see the lift coefficient change and also the drag coefficient on the right top of the plot. And the graph at the middle is the cross-section of our 3D models. So now Tristan will present our experimental setup. I'll pass it to him.
Thank you, Yonghao. I will now be walking us through the NACA 0012 model setup, which we use to test airfoil performance under different conditions. From the pictures, you can see, starting from the left, that our setup includes a fog machine to generate visible airfoil patterns around the airfoil, and then an airfoil model mounted on the tunnel for stability during testing, and video recordings captured at angles of attack ranging from 0 degrees to plus or minus 20 degrees in 5-degree increments. These recordings help us analyze aerodynamic behavior at each angle to enhance visibility, which we use a black drape to reduce glare and a flashlight position above to eliminate the airflow patterns. This allows us to clearly observe the fog flow as it moves towards the airflow, providing a visual representation of airflow dynamics. And then the airfoil is securely mounted in the test chamber, ensuring consistent and reliable testing conditions. I'll now be passing it on to Noah for our flow patterns at 0, 5, and 10 degrees.
Thanks, Tristan. So at 0 degrees, there is no separation and there's steady flow over the airfoil. The streamlines are mostly straight and parallel and remain attached to the surface. And the pressure distribution is relatively balanced between the top and bottom surfaces. At 5 degrees, separation still remains minimal and the flow is steady. The streamlines begin to curve at the tip of the airfoil, and lift is indicated by low pressure on the top surface and high pressure on the bottom. At 10 degrees, more prominent effects can be seen on the airfoil. There are significant curves on the streamlines, and the streamlines on the upper surface are tighter and closer together than the bottom. Lift is substantially higher, but drag forces increase as well, leading to localized separation at the trailing edge. These results confirm the expected behavior of the airfoil and agree with our proposition. Oh god, I messed that up. Cut that. And now I'll pass it over to Vanessa to cover angles of attack.
Hello, I'm Vanessa. At these negative numbers, -5 and -10 degrees, our observations, they're reversed similar to the positive angles that Noah just discussed. And although for -5 degrees, we start to see a creep in the disturbance of flow, it still remains steady and with little to no separation. At -10 degrees, there's more of an obvious larger flow disturbance that's clearly seen, and so concludes that setting our angles, whether negative or positive, we see a direct visual flow on separation, which is expected according to airfoil characteristics. Next, Kevin will introduce these higher angles of attack.
Yeah, so on the left is the airfoil at an angle of attack of 15 degrees. The airfoil remains attached along the surface, the airflow remains attached along the surface with no visible signs of separation. The flow is also smooth and steady, indicating minimal turbulent and stable performances. The diagram on the bottom left illustrates steady airflow with attached streamlines representative of this condition. The right image shows an angle of attack of 20 degrees. The airflow visibly detaches from the upper surface of the airfoil, indicating separation. Additionally, the absence of visual vortices suggests that while the flow is disturbed and isn't turbulent, the stall conditions are near but not fully developed. The diagram on the bottom right demonstrates the beginning of these stages of stall, showing flow separation. And now Dev will talk about the next slide.
Hi, so I'm going to talk about the streamline manifold. Initially, we designed a rake style manifold as seen on the left. There's different iterations of that. However, these designs overlook the bluff body wake. The cylindrical geometry of the rakes would disrupt the streamlines, creating turbulence, and that turbulence effect would render the streamlines unusable for accurate visualization. If you look at the bottom right picture, if the streamlines began at the back end of the cylinder, they would appear chaotic and unrepresentative of the actual flow due to wake effects. And you can see on the diagrams on the top right that they show the wake of both a streamlined body and a bluff body. And the whole point of the manifold is to preserve streamline integrity because it's upstream of the airfoil model in the test section. So using Cody's advice, we decided to move to a more streamlined manifold design. Here's the final design and manufactured models that we used. And during testing, we noticed that there's some turbulence visible in the streamlines. We tried trimming the little nozzles at the trailing edge of the manifold to see if that would improve the flow, but it had little to no impact. And we came to the conclusion that the manifold thickness near the leading edge was too large and it caused flow separation at the leading edge, which affected the streamlines negatively. And in retrospect, a much smaller and shorter manifold would have been a better solution. We could have also guided the smoke more efficiently on the internal side of the manifold to increase thickness and visibility of streamlines. And something like the SolidWorks sketch, the green part of the SolidWorks sketch would be improvement to our current design. And that design would minimize the leading edge thickness and reduce the separation effects, which would improve streamline clarity. I'll pass it on now.
Thank you, Dave. For our final observations, we find the flow visualization in airfoil models help us to understand the behavior of boundary layers and also determine the location where flow separation occurs that can lead to stalling or increased drag. And based on that, we can use the following techniques to minimize the drag or maximize the lift. The first approach is to the active flow control using suction technique. It can effectively control the development of boundary layer and also delay flow separation at a higher angle of attack. This is achieved by injecting a small amount of energy into the system. And another approach is by employing vortex generators. This will cause the kinetic energy of the boundary layer increase, which also helps delay flow separation, particularly at a higher angle of attack. And this is the end of our presentation. Thank you for listening.